Some of the light reaching your eyes tonight began its journey before your great-grandparents were born, traveling from stars that have already gone dark, already collapsed or scattered into dust, though their glow continues onward through the emptiness, a kind of cosmic afterimage that asks nothing of you but stillness. There is something quietly staggering in this, that the sky above is not a map of what exists, but a layered record of what once was, each point of light arriving from a different depth of time, some ancient, some merely old, all of it mingling into a single view that belongs only to this moment, this exact place where you happen to be resting. If these slower evenings bring you any ease, staying close to this channel means more will find their way to you. And so, gently, we begin. On a clear night, when the air has settled and the last colors of sunset have faded into that deep and particular blue that comes before true darkness, there is a moment that has repeated itself across all of human history, a moment so simple and so unremarkable that we rarely pause to consider how ancient it truly is. It is the moment when a person steps outside, perhaps onto a porch or into a garden or simply away from the lights of a dwelling, and lifts their face toward the sky. The neck tilts back gently, the eyes adjust, and there, scattered across the darkness like seeds thrown by some impossibly patient hand, are the stars. This act requires no special knowledge, no equipment, no preparation beyond the willingness to stand still for a moment and look upward. It is available to nearly everyone who has ever lived, and it connects us, in ways both obvious and subtle, to every generation that came before. The earliest recorded attempts to make sense of this view, to organize the scattered lights into something comprehensible and useful, stretch back thousands of years into human history. Around 1200 years before the Common Era, give or take a century or two depending on which clay tablets we examine and how we interpret their worn cuneiform markings, Babylonian astronomers were already naming patterns in the sky. They looked up from the flat lands between the Tigris and Euphrates rivers, from cities whose names have become synonymous with antiquity, and they saw shapes. They saw a lion, a bull, a scorpion with its curving tail. They saw figures from their mythology and their daily lives, and they gave these patterns names that would persist, in various translations and adaptations, for more than 3,000 years. When you look up tonight and find the constellation we call Leo, or Taurus, or Scorpius, you are using a system of organization that began in the minds of people who lived before the Trojan War, before the founding of Rome, before so much of what we consider ancient history had even begun to unfold. The names have changed somewhat, filtered through Greek and Latin and Arabic and eventually into the languages we speak today. But the essential act of grouping those particular stars together, of seeing that particular lion or that particular scorpion, began in Bronze Age Mesopotamia. Several centuries later, around 129 years before the Common Era, a Greek astronomer named Hipparchus of Nicaea undertook what may have been the most ambitious cataloguing project of the ancient world, working from the island of Rhodes, using instruments that would seem impossibly crude by modern standards but were state-of-the-art for their time. Hipparchus set about creating a systematic list of the stars visible to the naked eye. He recorded their positions, measured their brightness using a scale of his own devising that we still use in modified form today, and compiled everything into a document that would influence astronomy for centuries to come. His catalogue contained approximately 850 stars, each one carefully noted and positioned relative to the others. It is worth pausing for a moment to consider what this meant. The patience and dedication required to spend night after night, year after year, watching the sky with such careful attention. Hipparchus could not take a photograph. He could not consult a computer. He had to stand or sit in the darkness, waiting for clouds to clear, waiting for the proper season when certain stars would be visible, and record everything by hand, by candlelight or oil lamp, squinting at wax tablets or papyrus scrolls. 850 stars, each one a small act of devotion to understanding the universe overhead. The human eye, it turns out, is capable of seeing rather more than Hipparchus managed to catalogue, though not by as much as one might expect. On a truly clear night, from a location far removed from artificial light, where the air is clean and dry and the horizon stretches unobstructed in all directions, a person with good vision can perceive approximately 2,500 individual stars. This number varies somewhat depending on atmospheric conditions, on the acuity of the particular eyes doing the looking, on whether the moon is up and washing out the fainter points of light. But as a general figure, 2,500 is a reasonable estimate for what our unaided senses can detect of the stellar population. This is, considered from one angle, an impressively large number, a generous scattering of lights that takes real effort to count and even more effort to memorize. Considered from another angle, it is an almost impossibly small fraction of what is actually out there, a mere handful compared to the hundreds of billions of stars in our galaxy alone. But for most of human history, these 2,500 visible points of light were all we knew, and they were quite enough to inspire wonder and mythology and some of the most remarkable feats of navigation the world has ever seen. The Polynesian peoples who spread across the vast Pacific Ocean, colonizing islands separated by thousands of miles of open water, developed navigational techniques that relied heavily on the stars overhead. Beginning perhaps 3,000 years ago and continuing through more recent centuries, these voyagers set out in double-hulled canoes, crossing distances that would challenge modern sailors with modern equipment, and they did so by reading the sky. They memorized the rising and setting points of dozens of stars throughout the year. They noted which stars passed directly overhead at which islands, creating a kind of celestial map that corresponded to the physical geography of their ocean world. They observed the subtle differences in how stars appeared when reflected in calm water versus choppy seas. They built entire systems of knowledge around the assumption that the stars were reliable, fixed points of reference that would be in the same positions night after night, generation after generation. A navigator could teach his son or daughter the same star paths he had learned from his own parents, confident that the knowledge would remain accurate indefinitely. The stars, in the Polynesian understanding, were eternal guideposts, unchanging markers in a world of changing winds and currents and weather. This assumption of permanence, this trust in the constancy of the night sky, runs through nearly every human culture that has left records of its astronomical observations. The ancient Egyptians aligned their pyramids with certain stars. The builders of Stonehenge created sightlines to mark celestial events. Chinese astronomers kept meticulous records of the sky partly because changes in the heavens were thought to signal changes in the fortunes of emperors. In all of these traditions, the underlying belief was the same, that the stars represented something stable and eternal in a world of constant flux. The seasons changed, the years passed, civilizations rose and fell, but Orion still hunted across the winter sky, and the Seven Sisters still clustered together in their familiar grouping, and the North Star still pointed the way for travelers who had lost their bearings. This was a source of profound comfort. The idea that some things, at least, could be relied upon to remain as they had always been. Consider, for a moment, the three stars that form the belt of Orion, that distinctive row of almost equally spaced lights that serves as one of the most recognizable patterns in the entire sky. These three stars have been watched by humans for as long as humans have been watching anything. They were present in the sky above the African savanna when our earliest ancestors first developed the capacity for wonder. They were there when the pyramids at Giza were being constructed, and some scholars believe the pyramid's layout was designed to mirror their arrangement. They were there when Cleopatra stood on the banks of the Nile and made decisions that would change the course of Roman history. They were there when William Shakespeare wrote plays about star-crossed lovers and contemplated what it meant to be mortal. They were there when your grandmother was a young woman, looking up at the night sky and perhaps thinking about her future, about the people she would love and the places she would go. They are there tonight, right now, if you care to step outside and look for them, assuming the season and your location make them visible. The same three stars, in the same arrangement, keeping watch over the world as they have always done. There is something deeply reassuring about this continuity, this sense that we share the sky with everyone who has ever lived. The light falling on your eyes when you look at a familiar constellation is, in some meaningful sense, the same light that fell on the eyes of philosophers and farmers and kings and children throughout history. The patterns have not changed. The stars have not moved in any way perceptible to casual observation. They seem fixed, permanent, eternal in the way that very few things in human experience are eternal. We change, we age, we pass away, but Orion keeps hunting, and the dippers keep dipping, and the Southern Cross keeps pointing toward the pole for those who live beneath it. This is the gift that the night sky seems to offer, a window into something larger and more lasting than our individual lives. When we look up at a star on a clear evening, following this ritual that stretches back through countless generations, we tend to make an assumption so natural and so intuitive that it barely registers as an assumption at all. We believe that we are seeing the star as it currently exists, that the light reaching our eyes represents the star in its present state, shining away up there in the darkness at this very moment. The star appears to us as a friendly presence, a small and distant light that nonetheless feels somehow connected to our experience of looking at it. We imagine, if we imagine anything at all about the star's existence, that it is keeping watch over us in some vague and pleasant sense, a fixed point in the heavens that will continue to shine for as long as anyone cares to look. The star is there, present and alive, doing whatever it is that stars do, and we are here, looking up at it, participating in the oldest and simplest of human relationships with the cosmos. This assumption, this innocent and comforting belief that what we see is what is, has served humanity well for most of our history. It allowed the Babylonians to name their constellations with confidence, knowing that future generations would see the same shapes. It allowed Hipparchus to compile his catalogue, trusting that the stars he recorded would remain in their positions for others to verify. It allowed the Polynesian navigators to teach their children the old star paths, secure in the knowledge that the stars would continue to guide the way. It allowed your grandmother to look at the same Orion her grandmother had looked at, feeling that sense of connection across time that the night sky uniquely provides. The assumption was practical, it was beautiful, and it was, in all the ways that mattered for daily human life, perfectly adequate. The stars looked permanent, and so we treated them as permanent, and this worked well enough for thousands upon thousands of years of human civilization. But there is something that the casual stargazer, Standing in a garden on a clear evening and looking up at the familiar patterns overhead does not typically consider something that becomes apparent only when we begin to think carefully about what light actually is and how it travels through the vast distances of space. The assumption of presence, of seeing the star as it currently exists, contains a subtle but profound misunderstanding, one that transforms the simple act of stargazing into something rather more poignant and strange than it might initially appear. The light that reaches your eyes has been traveling for a very long time indeed, crossing unimaginable distances at a speed that, while very fast by earthly standards, is nonetheless finite and measurable. This simple fact has consequences that the Babylonians could not have known, that Hipparchus could not have suspected, that even the brilliant navigators of Polynesia had no way of anticipating. The night sky, it turns out, is not quite what it seems, and the evening ritual of looking up connects us not only to our ancestors but to questions about time and distance and existence that become more interesting the more carefully we consider them. In the year 1676, in the city of Copenhagen, a young Danish astronomer named Ole Romer was engaged in what might seem, at first consideration, to be rather routine work, the sort of careful and patient observation that fills the logbooks of observatories without ever troubling the minds of those who do not peer through telescopes. He was timing the eclipses of a small moon, one of the 4 great satellites of Jupiter that Galileo had discovered some 66 years earlier, a moon we now call Io, which orbits its enormous parent planet once every 42.5 hours or so, disappearing behind Jupiter's bulk with clockwork regularity, or at least with what should have been clockwork regularity, which is precisely where our story begins to unfold in its quiet and consequential way. Romer had been appointed to work at the Royal Observatory, which in those days was situated at the Rundetårn, the Round Tower, a building that still stands in Copenhagen today, its spiral ramp winding upward to an observing platform where, on clear nights, one might imagine the young astronomer settling in to watch Jupiter's moons perform their endless celestial dance. The observations he was making were not idle curiosity but practical necessity, for accurate tables of Io's eclipses could serve as a kind of cosmic clock, useful for determining longitude at sea, a problem of tremendous importance in an age when ships regularly became lost and sailors perished for want of knowing precisely where upon the ocean they happened to be. What Romer noticed, after months of careful record-keeping, was something peculiar, something that did not quite fit the expected pattern. A small but persistent discrepancy that a less attentive observer might have dismissed as measurement error or atmospheric disturbance or some other convenient explanation. He found that when Earth, in its own orbit around the Sun, was moving toward Jupiter, the eclipses of Io seemed to occur slightly earlier than predicted, and when Earth was moving away from Jupiter, those same eclipses seemed to occur slightly later, as though the cosmic clockwork were somehow affected by the changing distance between the 2 planets. Now, one might pause here and consider how such an observation could be explained, and Romer, being a thoughtful person, arrived at a remarkable conclusion, one that had never before been demonstrated through measurement, though some natural philosophers had speculated about it in earlier centuries. He proposed that light itself must travel at a finite speed, that it requires time to cross the vast emptiness of space, and that when Earth is farther from Jupiter, the light carrying news of Io's eclipse must journey a greater distance before reaching our eyes, causing the eclipse to appear delayed even though it occurred, in reality, precisely on schedule. This was, if you allow yourself to appreciate its significance while remaining comfortably drowsy, a rather profound realization. for it had been assumed by many learned people that light either traveled instantaneously or moved so swiftly as to make any delay utterly imperceptible across the distances then imaginable. Romer's observations suggested otherwise, and he calculated, from the accumulated delays and advances in Io's eclipses, that light required approximately 22 minutes to travel across the full diameter of Earth's orbit around the Sun, the distance we would later come to call 2 astronomical units, which is to say, twice the average distance from Earth to the Sun. His calculation, as it happens, was not perfectly accurate, for the true figure is closer to 16.5 minutes. But consider how remarkable it is that he came so close, within roughly 30% of the correct value, using nothing more than a telescope, a clock, careful record-keeping, and the patient accumulation of data over many months of observation. The instruments of his day were crude by modern standards. The precise distances between planets were not yet well established, and yet Romer managed to demonstrate something that had eluded philosophers since ancient times: that light possesses a definite and measurable velocity, that seeing is not instantaneous, that there is a delay, however brief, between the moment an event occurs and the moment its light reaches our eyes. The response to Romer's announcement was, as often happens with ideas that challenge established understanding, somewhat mixed, and not everyone was persuaded by his reasoning. Giovanni Cassini, the Italian-born astronomer who directed the Paris Observatory and who had himself spent many years observing Jupiter's moons with great skill and dedication, was among those who expressed skepticism. Cassini had earlier entertained similar ideas about light having a finite speed, but he ultimately rejected Romer's interpretation, preferring to attribute the timing discrepancies to some other cause, perhaps some irregularity in Io's orbit that had not yet been properly accounted for, or some systematic error in the observations themselves. This disagreement was not acrimonious in the manner of some scientific disputes, but rather reflected the genuine uncertainty that existed at the time about how to interpret the available evidence. Science proceeds in this fashion more often than dramatic accounts might suggest, with reasonable people examining the same observations and reaching different conclusions, until eventually new evidence or new methods of analysis settle the question one way or another. In the case of light's velocity, confirmation would come gradually over the following decades and centuries, through ever more refined measurements and entirely different experimental approaches, until the finite speed of light became not just accepted but fundamental to our understanding of the physical world. Today, we know the speed of light with extraordinary precision, having measured it using methods that Romer could scarcely have imagined, employing lasers and atomic clocks and distances calibrated to fractions of a meter. The value, expressed in the units we commonly use, is 299,792 kilometers per second, or if you prefer, very nearly 300,000 kilometers in the time it takes to draw a single breath, an almost incomprehensible velocity that nothing in the universe can exceed, as far as we have ever been able to determine. This number, this particular speed, is not merely a curiosity or a bit of scientific trivia to be memorized and then forgotten. It is woven into the very fabric of the universe, appearing in the equations that describe how matter and energy behave, how space and time relate to one another, how the cosmos operates at its most fundamental level. But for our present purposes, as we settle into this gentle exploration of distant stars and ancient light, the most important thing to understand is simply this: that light takes time to travel, and the farther it must journey, the more time that journey requires. Consider, As a beginning, our own sun, that familiar yellow star that warms our days and whose absence defines our nights. The sun lies approximately 150 million kilometers from Earth, a distance so vast that it defies easy comprehension, yet almost trivially small compared to the distances between stars. Light departing the sun's surface, traveling at that tremendous speed we have just discussed, requires 8 minutes and 20 seconds to reach us here on Earth, which means that the sunlight warming your face, should you be sitting by a window on a pleasant afternoon, departed the sun some 8 minutes before you felt its gentle heat. This delay is brief enough that it rarely matters in our daily lives, and yet it carries within it a curious implication, which is that we never see the sun as it is right now, in this present moment, but only as it was 8 minutes and 20 seconds ago. If the sun were to suddenly vanish, which it will not, but speaking purely hypothetically, we would continue to see it shining in the sky for another 8 minutes, unaware that anything had changed, until the last of its light completed its journey to our eyes. We are always, in a sense, looking into the past when we look at the sun, though the past we see is so recent as to be inconsequential for most purposes. This observation about our sun is merely the first gentle step in understanding something far more profound, something that becomes apparent only when we consider objects much farther away than our modest local star. For if light takes 8 minutes to travel from the sun, how long might it take to arrive from stars that lie not millions but trillions of kilometers distant, stars so far away that even light, swift as it is, requires not minutes but years or centuries or millennia to complete the journey? To answer such questions, astronomers first had to determine just how far away the stars actually are, a problem that had vexed observers for centuries and which found its first definitive solution in the work of Friedrich Wilhelm Bessel, a German astronomer of remarkable skill and patience who, in 1838, accomplished what many had attempted and all had previously failed to achieve. Bessel measured the distance to a star. The star in question was 61 Cygni, a modest reddish point of light in the constellation of the Swan, not particularly bright or notable to casual observers, but interesting to astronomers because it moved perceptibly against the background of more distant stars over the course of years, suggesting that it might be relatively nearby as stars go. Bessel selected it for precisely this reason, hoping that its proximity would make the measurement he intended to perform just barely possible with the instruments available to him. The technique Bessel employed is called stellar parallax, and it relies on the same principle that allows us to perceive depth with our two eyes. Hold a finger before your face and alternately close your left eye and then your right, and you will notice that your finger appears to shift position against the background, even though it has not moved at all. The apparent shift occurs because your two eyes view the finger from slightly different angles, and the closer the finger is to your face, the larger this shift appears. Bessel reasoned that if Earth occupies different positions in its orbit around the Sun over the course of a year, then nearby stars should appear to shift slightly against the background of more distant stars, in the same way that your finger shifts against the wall behind it when viewed from different angles. The size of this shift, called the parallax angle, would reveal the star's distance, with larger shifts indicating closer stars and smaller shifts indicating more distant ones. The difficulty, and it was a considerable difficulty indeed, was that even the nearest stars are so enormously far away that their parallax angles are extraordinarily tiny, less than a single arc-second for any star in the sky, which is to say, less than 1/3600th of a degree, a shift so small that it had escaped detection by every previous attempt. Bessel succeeded where others had failed through a combination of superior instruments, meticulous technique, and the sort of patient dedication that allows one to make the same observation night after night, month after month, gradually accumulating enough data to tease a faint signal from the noise of atmospheric distortion and measurement uncertainty. What Bessel found, after many months of careful work, was that 61 Cygni exhibited a parallax angle of about 1/3 of an arc-second, which corresponded to a distance of approximately 10 light-years, though the modern value is slightly closer to 11. A light-year, as you may know or may soon discover as you drift towards sleep, is the distance that light travels in 1 year, which works out to roughly 9.5 trillion kilometers. A number so large that it serves better as a unit of measurement than as something to be truly grasped by the human mind. Bessel's measurement was confirmed by other astronomers observing other nearby stars, and it soon became clear that even the closest stars to our Sun lie several light-years distant, while the vast majority lie tens or hundreds or thousands of light-years away, and some, the faint smudges of distant galaxies that larger telescopes would later reveal, lie millions or even billions of light-years from Earth. And here we arrive at the quiet realization that Romer's discovery, combined with Bessel's measurement, presents to us if we consider it gently and without alarm. If light travels at a finite speed, and if stars lie at such tremendous distances, then the light we see when we look at the night sky is not the light of the present moment but the light of the past, light that departed its source years or centuries or millennia ago and has been traveling through the darkness of space ever since, carrying with it an image of what that source looked like at the moment of departure, an image that may no longer correspond to what exists there now. The implications of this realization would unfold slowly over the following decades and centuries, as astronomers measured ever greater distances and contemplated ever deeper stretches of cosmic time. But for now, as you rest here in the quiet of the evening, it is enough to hold this one thought gently in your mind: that light takes time to travel, that the stars are very far away, and that therefore what we see when we look up at the night sky is not a snapshot of the present but a mosaic assembled from different moments in the past, each star's light carrying its own history, its own story of the long journey through darkness to reach our waiting eyes. When we speak of measuring the distances to stars, we are really speaking of one of the most patient and methodical undertakings in all of human inquiry, a slow accumulation of techniques refined over centuries, each one reaching a little further into the dark than the one before, and each one revealing, in its own quiet way, just how vast the spaces between things truly are. The astronomers who developed these methods were not seeking drama or spectacle, but rather something far more humble, which was simply to know, with some reasonable certainty, how far away the lights in the sky actually were, and in pursuing that knowledge they gave us tools that now allow us to peer across distances so immense that the light arriving at our eyes tonight may have been traveling since before there were eyes anywhere in the universe to receive it. The first and most fundamental of these methods is called parallax, and it works on a principle so simple that you can demonstrate it to yourself right now, if you are not already drifting towards sleep, by holding up your thumb at arm's length and closing first one eye and then the other, watching how your thumb appears to shift against the background. This apparent shift, this small jump from one position to another, is parallax, and it occurs because your two eyes are looking at the same object from slightly different positions in space, separated by the few centimeters between them. The closer the object, the more dramatic the shift appears, and the farther away the object, the smaller and more subtle the apparent movement becomes. until at some great distance the shift is so tiny as to be imperceptible, and the object seems fixed no matter which eye you use. Astronomers realized, quite sensibly, that they could apply this same principle to the stars, but instead of using the separation between two eyes, they would use something rather larger, which was the diameter of Earth's orbit around the Sun. Over the course of a year, as Earth traces its great elliptical path around our star, we shift our position by some 300 million kilometers from one side of the orbit to the other, and this provides a baseline for measurement that is enormously wider than any distance we could achieve here on the planet's surface. By observing a star in January, and then observing that same star again in July, when Earth has traveled to the opposite side of its orbit, astronomers can measure the tiny apparent shift in the star's position against the more distant background stars, which are so far away that they show no shift at all and serve as a kind of fixed reference grid. The angle of this shift, called the parallax angle, is extraordinarily small for even the nearest stars, measured in fractions of a second of arc, which is itself a fraction of a degree, and detecting such minute angles required instruments of great precision and observers of great patience and care. For nearby stars, those within roughly 1,000 light-years of us, parallax remains our most direct and reliable method for measuring distance, and modern space telescopes have refined these measurements to remarkable accuracy, mapping the positions and distances of over 1 billion stars in our galaxy with parallax angles measured to millionths of a degree. But the universe extends far beyond 1,000 light-years, and for the more distant stars, and for the galaxies that lie beyond our own, the parallax angles become so vanishingly small that even our finest instruments cannot detect them, and we must turn to other methods, less direct but still wonderfully clever, which astronomers call standard candles. The idea behind a standard candle is beautifully simple, and it rests on the observation that if you know how bright something actually is, and you measure how bright it appears to be, you can work out how far away it must be, since light dims with distance in a predictable way, following what is called the inverse square law. If you move twice as far from a light source, it appears 4 times dimmer, and if you move 10 times as far, it appears 100 times dimmer, and this reliable relationship between distance and apparent brightness allows us to reach across distances where parallax fails us entirely. The challenge, of course, is knowing how bright something actually is, which astronomers call its intrinsic luminosity. And this is where a young woman named Henrietta Swan Leavitt made one of the most important discoveries in the history of astronomy, working quietly at the Harvard College Observatory in the early years of the 20th century. Leavitt was employed as what was then called a computer, which in those days meant a person, usually a woman, who performed the painstaking mathematical calculations and careful measurements that the male astronomers required for their research. She was paid 30 cents an hour for this work, and she spent her days examining photographic plates of the night sky, comparing images taken at different times, and cataloguing the properties of thousands upon thousands of stars. Her task, assigned to her by the observatory's director, was to study variable stars, those stars whose brightness changes over time in regular, repeating patterns, dimming and brightening in cycles that might last days or weeks or months. In particular, Leavitt studied variable stars in the Magellanic Clouds, which are 2 small galaxies, satellite companions to our own Milky Way, visible from the southern hemisphere as faint cloudy patches in the night sky. She examined the photographic plates with extraordinary care, identifying and measuring 1,777 variable stars in these distant clouds, recording their periods of variation and their apparent brightnesses. And slowly, methodically, she began to notice a pattern emerging from the data. The stars she was studying belonged to a class called Cepheid variables, named after the star Delta Cephei, which had been among the first of its type to be identified. And what Leavitt discovered was that there was a clear relationship between how long a Cepheid took to complete one cycle of brightening and dimming, its period, and how luminous it actually was. The longer the period, the brighter the star, and this relationship was so consistent and so reliable that if you could measure the period of any Cepheid variable anywhere in the universe, you could determine its intrinsic brightness, and from that, using its apparent brightness as seen from Earth, you could calculate its distance. This period-luminosity relationship, as it came to be known, was published in 1912, and it transformed astronomy in ways that Leavitt herself, who died of cancer in 1921 at the age of 53, did not live to fully see. Her discovery provided the first reliable method for measuring distances to objects far beyond the reach of parallax, and it was this method that Edwin Hubble would later use to demonstrate that the Andromeda Nebula was not a cloud of gas within our own galaxy, as many believed, but an entirely separate galaxy, millions of light-years away, and that the universe was vastly larger than anyone had imagined. Henrietta Swan Leavitt, working for 30 cents an hour, measuring photographs one careful observation at a time, had given humanity a tool to measure the cosmos, and her name should be remembered alongside the most celebrated figures in the history of science, though for many decades it was not. With these methods, parallax for the nearby stars and standard candles for the more distant ones, astronomers have mapped the distances to countless objects in the night sky, and in doing so they have revealed something that takes some time to fully appreciate, which is that when we look at a star, we are not seeing it as it is now, but as it was when the light that reaches our eyes first left its surface. Light travels at a finite speed, very fast by earthly standards but still limited, covering roughly 300,000 kilometers in each second. And even at this tremendous speed, the light from distant objects takes time to reach us, and during that time, anything might have happened at its source. The star might have changed, might have grown older, might have exploded, might have vanished entirely, and we would not know, could not know, until the light carrying news of that change had traveled all the way across the intervening space to where we stand. Consider Proxima Centauri, which is the nearest star to our own Sun, a small red dwarf star located in the Alpha Centauri system, at a distance of just 4.24 light-years from Earth. This means that the light we see from Proxima Centauri tonight left its surface 4 years and a little over 2 months ago, and we are seeing it not as it is in this present moment, but as it was during what for us was the recent past. If something were to happen to Proxima Centauri right now, this very instant, we would continue to see it shining in the sky, unaware of any change, for more than 4 years, until the light from that event finally reached us. For years is not very long, as these things go, and Proxima Centauri is close enough that the delay feels almost negligible, a brief lag between the event and our observation of it. But as we look to more distant stars, the delays grow longer, and the windows into the past grow deeper. Polaris, the North Star, which has guided travelers for centuries, sits at a distance of approximately 430 light-years from Earth, and this means that the light we see from Polaris tonight began its journey during the Renaissance, when Leonardo da Vinci was sketching his designs for flying machines and Copernicus was formulating his model of the solar system. The photons entering your eyes, if you were to look at Polaris on a clear night, have been traveling through space since roughly the year 1595, crossing the void while empires rose and fell, while the entire modern age unfolded on this small planet. And only now, after 4 centuries of travel, are they completing their journey. When we look at Polaris, we are looking at a star as it was during the time of Shakespeare, and whatever Polaris is doing now, in this present moment, we will not see for another 430 years. Betelgeuse, the red supergiant star that marks the shoulder of Orion, lies at a distance of approximately 650 light-years, and the light we see from it tonight left during the 1370s, when the Black Death was still a recent memory in Europe, when the Ming dynasty was newly established in China, and when the great cathedrals of the medieval period were standing newly built or still under construction. Betelgeuse is an old star, nearing the end of its life, and astronomers have long speculated that it might explode as a supernova at some point, perhaps soon in astronomical terms, which means within the next 100,000 years or so. For all we know, it may have already exploded centuries ago, and the light from that cataclysm is still on its way to us, traveling through the dark, and we will continue to see Betelgeuse as a steady point of orange light until the news of its death arrives. There is something peaceful in this. Perhaps the idea that the stars we see are preserved for us in light, held in a kind of gentle suspension, their present states unknown and unknowable, only their pasts available to us, like letters sent long ago that are still in transit. Deneb, the bright star at the tail of Cygnus the Swan, lies at a distance of roughly 2,600 light-years, and its light began its journey during the Bronze Age, when the great civilizations of Mesopotamia and Egypt were flourishing, when Stonehenge was still in active use, and when the written word itself was a relatively new invention. The light from Deneb has been traveling since before the Trojan War, if it happened at all, since before Rome was founded, since before the Buddha or Confucius or Socrates were born, and it arrives at our eyes tonight carrying an image of a star as it was when human history was just beginning to be recorded. We look at Deneb and we see the Bronze Age, preserved in light, still arriving. And beyond the individual stars of our own galaxy, there are the other galaxies, the great island universes that drift through the larger cosmos, and the nearest of these large galaxies is Andromeda, a spiral galaxy much like our own, visible to the naked eye on dark nights as a faint smudge of light. Andromeda lies at a distance of approximately 2.5 million light-years, and the light we see from it tonight left its countless stars during the Pliocene epoch, long before Homo sapiens existed, when our ancestors were small and distant branches on the hominid family tree, when the genus Homo had not yet emerged, when the African savannas were home to creatures that were not yet human but were on the long, slow path that would eventually lead to us. The light from Andromeda has been traveling since before there were people to wonder about it, since before there were minds that could ask questions about the night sky, and it arrives now to be gathered by telescopes and cameras and curious eyes that would not exist for millions of years after it began its journey. Each star, each galaxy, each faint point of light in the sky, is a window into a different moment in cosmic history, and when we look up at the night sky, we are not seeing the universe as it is, but as it was, a vast collection of moments from different times, all arriving together at this single instant, layering atop one another like pages in a book. The nearby stars show us the recent past, a few years or decades, while the more distant stars show us centuries and millennia, And the farthest galaxies show us the universe as it was billions of years ago, when it was younger and different, when the stars themselves were different, when everything was closer together and the great expansion of space had not yet carried things so far apart. It is a gentle thing to consider, as you rest here, that the light falling on the earth tonight has been traveling for such various durations, that some of it began its journey while you were a child and some of it began before there were children anywhere, before there was an earth for them to be born on, before the sun had formed from its collapsing cloud of gas and dust. The light arrives, patient and unhurried, and we receive it, and in receiving it we touch, however lightly, moments that are otherwise lost to us, preserved only in these ancient photons that have crossed the dark to reach us. And so we arrive at a thought that may have been forming quietly in your mind, a question that settles into place with the gentleness of evening mist, and yet changes how we might regard the night sky from this moment forward. The question is simple enough to state, and it goes something like this: could some of the stars we see tonight, those steady points of light that seem so permanent and fixed in their ancient patterns, have already ceased to exist, their fires already gone cold in the vast darkness, even as their light continues its unhurried journey toward our eyes? This is not a fanciful notion or a piece of poetic license, but rather a genuine possibility that emerges naturally from the physics of starlight and the finite lives that stars must lead. And to understand why this might be so, we need to consider how long stars actually live and how those lifetimes compare to the distances their light must travel to reach us here on Earth. Stars, you see, do not burn forever, though they certainly give that impression when we observe them on the timescale of a single human life, or even many generations of human lives. What appears unchanging to us is simply change occurring at a pace too slow for our brief existence to perceive, rather like watching the hour hand of a clock and finding it impossible to detect any movement at all, even though we know with certainty that it must be moving. Our own sun, that familiar yellow star that has warmed every face that has ever lived and illuminated every afternoon since afternoons began on this planet, has a total lifespan of approximately 10 billion years, a span of time so vast that it seems almost indistinguishable from eternity when measured against the few decades we each are given. The Sun formed roughly 4.5 billion years ago from a collapsing cloud of gas and dust, which means it is now somewhere near the middle of its life, with another 5 billion years or so remaining before it exhausts the hydrogen fuel in its core and begins the slow transformation that will eventually see it swell into a red giant star and then fade into a cooling ember called a white dwarf. 5 billion years of remaining solar fuel is, of course, an almost unimaginable luxury of time, more than enough to see out whatever future Earth and its inhabitants might have. And so our Sun poses no immediate concern regarding the question of stars that might have died without our knowledge. But the Sun is a rather modest star as stars go, and not all stars share its patient temperament or its generous allotment of cosmic time. Some stars burn with far greater intensity, consuming their nuclear fuel at prodigious rates that would exhaust a star like our Sun in a mere fraction of its expected lifetime. These are the massive stars, the great blue and white giants that blaze with luminosities tens of thousands or even hundreds of thousands of times greater than our Sun, and their fierce output comes at a steep price, for the faster they burn, the sooner they must inevitably burn out. Consider Eta Carinii, an extraordinary star system located in the southern constellation of Carina, visible to those who find themselves beneath sufficiently dark skies in the southern hemisphere. Eta Carinii is one of the most massive and luminous stellar systems known to astronomers, with the primary star estimated to contain perhaps 100 times the mass of our Sun and shining with a brilliance that defies easy comprehension. Such a star does not enjoy the leisurely lifespan of our modest yellow Sun, but instead races through its nuclear fuel in a matter of mere millions of years rather than billions, burning so brightly and so furiously that its entire existence from birth to death occupies less time than some geological epochs here on Earth. A star like Eta Carinii lives fast and dies spectacularly, and though it may briefly outshine entire galaxies when its final moment arrives, that moment arrives far sooner than we might expect given our experience with the steady, reliable Sun. The understanding that stars have definite lifespans that depend upon their mass and luminosity emerged gradually through the early decades of the 20th century, and a crucial piece of this understanding came in the form of what is now called the Hertzsprung-Russell diagram. This diagram, which has become one of the most important tools in stellar astronomy, was developed independently by two astronomers working in different countries and speaking different languages, a Danish chemist named Ejnar Hertzsprung in 1911 and an American astronomer named Henry Norris Russell in 1913. Each man, working from his own observations and analysis, arrived at the insight that if you plotted stars on a graph according to their luminosity and their surface temperature, or equivalently their color, the stars did not scatter randomly across the diagram but instead fell into distinct patterns and groupings. Most stars clustered along a diagonal band that came to be called the main sequence, running from hot, bright blue stars in one corner to cool, dim red stars in the opposite corner. And our Sun sits comfortably along this main sequence as a perfectly ordinary yellow star of moderate temperature and moderate brightness. What the Hertzsprung-Russell diagram revealed, once astronomers had time to study its implications, was nothing less than the life cycle of stars laid out in graphical form. A star's position on the diagram tells us not only about its current state but also about its past and future. For stars move across the diagram as they age, tracing predictable paths that depend upon the mass they were born with. A massive blue star sitting high on the main sequence is living a brief and brilliant life that will end in cosmic catastrophe, while a small red star sitting low on the main sequence is conserving its fuel with such care that it may continue to shine long after our Sun has faded, perhaps for hundreds of billions of years. Far longer than the current age of the universe itself. The diagram that Hertzsprung and Russell independently created became a kind of map of stellar mortality, showing us that the brightest and most spectacular stars are also the most ephemeral, while the dimmest and most easily overlooked are the ones that will ultimately endure. Among the bright stars that ornament our winter and summer skies, depending upon which hemisphere claims your allegiance, is Rigel, the brilliant blue-white star that marks the foot of Orion the Hunter and serves as one of the most luminous stars visible to the unaided eye. Rigel lies approximately 860 light-years from Earth, which means that the light entering your eyes when you gaze upon it departed from that distant sun some 860 years ago, during an era when medieval cathedrals were rising across Europe and the Mongol Empire was beginning its expansion across the Asian steppes. Rigel is a blue supergiant star, significantly more massive than our Sun and burning with an intensity that places it among the brightest stars in our region of the galaxy. And stars of this type have estimated lifespans of only 10 to 20 million years. A cosmic eye blink compared to our Sun's 10 billion-year tenure. Rigel is thought to be a relatively young star, only 8 to 10 million years old, which suggests it still has some millions of years remaining before its fuel runs out. But the arithmetic is close enough to give one pause. The physics of stellar death received a profound contribution in 1930 from a 19-year-old Indian physicist named Subrahmanyam Chandrasekhar, who was traveling by steamship from India to England to begin graduate studies at Cambridge University. During that long sea voyage, with time to think and calculate, Chandrasekhar worked through the mathematics of what happens to a star when it exhausts its nuclear fuel and can no longer support itself against the inward crush of its own gravity. For stars like our Sun, the end would come as the core collapsed and electrons were squeezed together until quantum mechanical effects prevented further compression, creating a dense, Earth-sized remnant called a white dwarf that would gradually cool over billions of years like a dying ember. But Chandrasekhar's calculations revealed something unexpected and rather troubling, which was that this quantum mechanical support had its limits. And if the collapsing stellar core exceeded a certain critical mass, approximately 1 4/10 times the mass of our Sun, the electrons would be unable to resist the gravitational crush and the collapse would continue toward some more extreme fate. This limiting mass became known as the Chandrasekhar limit, and its discovery opened the door to understanding the more dramatic endings that await massive stars. When Chandrasekhar presented his findings, some established physicists initially rejected the implications, finding it difficult to accept that matter could collapse to such extreme densities. But the young physicist's mathematics proved correct, and we now understand that stars above this limit must meet different fates, collapsing either into neutron stars, where protons and electrons are crushed together into a dense ball of neutrons, or into black holes, where the collapse continues beyond any known stopping point and the stellar material vanishes behind an event horizon from which nothing, not even light, can escape. The death of a star depends very much upon its mass, and the process unfolds differently for different classes of stellar objects. For stars similar to our Sun, the end comes gently, astronomically speaking, as the star sheds its outer layers in a slowly expanding shell of glowing gas called a planetary nebula, a name that has nothing to do with planets but was assigned in an earlier era when these round, fuzzy objects were first observed through telescopes and their nature was not yet understood. The planetary nebula drifts outward into space, carrying the processed elements that the star forged during its lifetime, while the exposed core remains behind as a white dwarf, gradually radiating away its stored heat over timescales that dwarf the current age of the universe. This is the quiet death, the gentle fading, the slow transition from shining star to cooling cinder, and it is the fate that awaits our Sun in approximately 5 billion years, long after whatever becomes of humanity and Earth. For massive stars, however, the end is far more violent and far more sudden. When a star with more than 8 or so times the mass of our Sun exhausts the hydrogen in its core, it does not simply fade away but instead begins a frantic sequence of nuclear burning, fusing heavier and heavier elements in a desperate attempt to stave off gravitational collapse. First helium fuses into carbon, then carbon into neon, then neon into oxygen, then oxygen into silicon, and finally silicon into iron, each stage lasting shorter than the one before, until the star finds itself with an iron core and nowhere left to go. Iron cannot be fused to release energy. It is the ash of nuclear burning rather than its fuel, and when the iron core grows too large, the star's support vanishes in an instant and the core collapses catastrophically inward, then rebounds outward in a titanic explosion called a supernova. For a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars, blazing across the cosmos with an intensity that staggers comprehension, before fading back into darkness and leaving behind either a neutron star or a black hole depending upon how much mass remains. And here, at last, is where the unsettling mathematics begins to take shape. For when we combine what we know about stellar lifetimes with what we know about the distances to the stars, we find that some distant massive stars may indeed be sending us light that takes longer to reach us than those stars have remaining to live. A blue supergiant burning through its fuel in 10 million years may sit 20 million light-years distant, and the light we see tonight would have left when that star still had 10 million years of fuel remaining, time enough for it to exhaust that fuel entirely before its light reaches our eyes. The star we observe appears healthy and bright, a vigorous young giant blazing in its prime, and yet the star itself may have already ended, may have already collapsed and exploded and scattered its elements across light-years of space, while we gaze unknowing at its ancient image, a stellar ghost still crossing the void. There are certain stars in the sky that astronomers regard with a particular kind of quiet attention, not because they are the brightest or the most beautiful, though some of them are quite beautiful indeed, but because these stars exist in a state of profound uncertainty, balanced somewhere between the light we can see and the fate we cannot know. These are the candidates, the stars that may already have concluded their long existence, whose final moments may have already occurred in the vast silence of space, though the news of their ending has not yet reached us across the tremendous distances that separate their position from our own. And so we watch them, these stars living on what we might gently call borrowed light, understanding that the photons arriving at our telescopes tonight could be the last chapter of a story that has already finished, or simply another unremarkable page in an ongoing tale that will continue for thousands or even millions of years yet to come. Perhaps the most famous of these uncertain stars, and certainly the one that has captured the most public attention in recent years, is Betelgeuse, which astronomers also know by its catalogue designation Alpha Orionis, marking it as the brightest star in the constellation of Orion the Hunter. Betelgeuse sits in the position of Orion's shoulder, a distinctly reddish point of light that even casual observers can pick out on a winter evening, and it has held this position in human awareness for as long as people have looked upward and given names to the patterns they found there. The name itself likely derives from an Arabic phrase, though the exact translation has been debated by scholars for centuries, with some suggesting it means the hand of Orion and others proposing alternative interpretations that have become muddled through the long history of transcription from one language to another. What is not debated, however, is that Betelgeuse is an enormous star, a red supergiant of truly remarkable proportions, so large that if you were to place it at the center of our own solar system, its outer atmosphere would extend beyond the orbit of Mars and possibly reach as far as Jupiter, swallowing Mercury and Venus and Earth and Mars in a great diffuse sphere of stellar material. Betelgeuse is approximately 700 light-years from Earth, though this distance carries its own uncertainty because measuring the precise distance to such stars involves considerable technical challenges, and different methods have produced somewhat different results over the years. What this distance means, in practical terms, is that the light we see from Betelgeuse tonight left that star approximately 700 years ago, during a period when medieval kingdoms still dominated Europe and the Great Plague had not yet swept across the continents. If Betelgeuse were to explode as a supernova at this very moment, the light from that catastrophic event would not reach Earth for another 7 centuries, and in the meantime, we would continue to see the star exactly as it appeared 700 years in our past, serene and reddish and seemingly eternal in the shoulder of the Hunter. This brings us to the events of late 2019 and early 2020, when Betelgeuse did something that captured worldwide attention and set off considerable speculation about whether the star's time had finally come. Beginning in October of 2019 and continuing into February of 2020, Betelgeuse began to dim in a manner that was genuinely unprecedented in the recorded history of astronomical observation. The star dropped to an apparent magnitude of approximately 1.614, which may not sound particularly dramatic when expressed in these technical terms, but which represented the faintest that Betelgeuse had ever been observed by human instruments in the centuries since people began keeping careful records of stellar brightness. For a star that typically ranks among the 10 brightest in the entire night sky, this dimming was remarkable, and it prompted a great deal of discussion about what might be happening. Some observers, particularly those outside the professional astronomical community, began to wonder aloud whether Betelgeuse was about to explode, whether the great dimming represented the final stages before a supernova that would briefly make the star visible even in daylight and leave behind either a neutron star or perhaps nothing at all. This speculation was understandable, given that Betelgeuse is precisely the type of star that will eventually end its existence in a supernova explosion, and given that the dimming seemed so unusual and so pronounced. The professional astronomical community approached the question with more caution, recognizing that while Betelgeuse will indeed explode someday, the timeline for such an event is measured in astronomical terms, which is to say that someday could mean tomorrow or could mean 100,000 years from now, and that stellar behavior in the final stages before collapse does not necessarily look the way we might expect from our limited observational experience. The resolution of the mystery came through careful observation, and particularly through the work of a researcher named Miguel Montages, who used the European Southern Observatory's Very Large Telescope in Chile to obtain detailed images of Betelgeuse during the dimming event. The Very Large Telescope, which despite its somewhat unimaginative name represents one of the most sophisticated astronomical instruments ever constructed, was able to resolve the disk of Betelgeuse with sufficient clarity to reveal what was actually happening. What Montages and his colleagues discovered was that the dimming was not caused by internal changes presaging an imminent explosion, but rather by a cloud of dust that had formed in front of the star, obscuring a portion of its light from our perspective here on Earth. The star had ejected material from its surface, as red supergiants are known to do periodically, and this material had cooled as it moved away from the stellar surface and condensed into dust particles that blocked the light traveling toward us. It was, in essence, a cosmic cloud passing in front of a cosmic lamp, and while it told us something interesting about the processes occurring in the outer atmosphere of this remarkable star, it did not indicate that Betelgeuse was about to meet its end. Betelgeuse remains in the sky tonight, still reddish, still enormous, still balanced somewhere in the long, slow process of stellar evolution that will eventually lead to its destruction, though that eventual destruction may be tens of thousands of years in the future or more. The star continues to pulsate in its slow, irregular rhythm, brightening and dimming over periods of months and years as its vast atmosphere expands and contracts, and astronomers continue to watch it with their instruments, adding each night's observations to the long accumulating record of data that may someday help us understand more precisely where Betelgeuse sits in its evolutionary journey. For now, it remains a candidate, a star that could already be gone or could persist for ages yet to come, sending its ancient light across the centuries to reach our waiting eyes. Another candidate for this uncertain category, and one with an even more dramatic observational history, is Eta Carinii, a stellar system located approximately 7,500 light-years away in the southern constellation of Carina. At this distance, the light we see from Eta Carinii tonight left that system around the time that ancient Mesopotamian civilizations were flourishing, long before the classical Greek period, long before the rise of Rome. in an era so distant that written records were still a relatively recent human innovation. This means that whatever is happening in Eta Carinii right now, whatever processes are occurring in that tumultuous stellar system at this present moment, will not become visible to observers on Earth for another 75 centuries, and the light we see tonight represents conditions that existed in an unimaginably distant past. What makes Eta Carinii particularly remarkable is that we have, within recorded astronomical history, witnessed this star undergo a catastrophic event of tremendous violence, an event that astronomers now call the Great Eruption of 1843. In that year, the astronomer John Herschel, son of the famous William Herschel who discovered Uranus, was conducting observations from the Cape of Good Hope in South Africa, and he recorded that Eta Carinii had brightened dramatically, becoming for a brief period the second brightest star in the entire night sky, exceeded only by Sirius. This was extraordinary because Eta Carinii is so much more distant than Sirius, which sits a mere 8.6 light-years from Earth, meaning that for Eta Carinii to appear nearly as bright as Sirius while being almost 1,000 times farther away, it had to be producing a truly staggering amount of light, an output that astronomers have calculated was roughly equal to the total luminosity of the Sun multiplied by a factor of several million. The Great Eruption was not a supernova, though it shared some characteristics with those terminal events, and Eta Carinii survived the experience, though in an altered state. What happened during those years of the 1840s was that the star ejected an enormous quantity of material, estimated at approximately 10 times the mass of our Sun, hurling this matter outward into space at tremendous velocities. This ejected material formed the structure we now call the Homunculus Nebula, a distinctive bipolar cloud of gas and dust that surrounds Eta Carinii and that can be photographed with modern telescopes, providing a visible record of that violent episode from nearly 2 centuries ago. The Homunculus Nebula continues to expand outward, its twin lobes growing slowly larger year by year, carrying within its structure the matter that was once part of the star itself, matter that was torn away and flung into space during those years of catastrophic instability. Eta Carinii today remains one of the most unstable stellar systems known to astronomy, a luminous blue variable star that continues to exhibit irregular variations in brightness and that could potentially undergo another major eruption at any time, or could proceed directly to a supernova explosion that would mark the end of its existence. Because of its enormous distance, 7,500 light-years, it is entirely possible that Eta Carinii has already exploded, that the supernova occurred millennia ago and that the light from that event is even now traveling through space toward Earth, destined to arrive at some point in the distant future and reveal to observers then living that the star they had known is no more. We cannot know, and so we continue to watch the light that departed so long ago, accepting the fundamental uncertainty that governs our relationship with objects at such tremendous distances. At a similar distance of approximately 8,000 light-years, there sits another candidate of considerable interest, a Wolf-Rayet star known by the catalogue designation WR104. Wolf-Rayet stars are a particular class of massive evolved stars characterized by strong stellar winds and by the exposure of their hot inner layers, having shed much of their outer hydrogen through the violent processes of stellar evolution. These stars are relatively rare, numbering perhaps only a few hundred known in our entire galaxy, and they represent a late stage in the lives of very massive stars, a stage that typically precedes the final collapse and supernova that will mark the end of their existence. WR104 drew particular attention in 1999 when observations using the Keck telescope in Hawaii revealed that the star and its binary companion are surrounded by a distinctive spiral structure of dust, rotating like a pinwheel as the two stars orbit around their common center of mass. This pinwheel pattern, captured in infrared observations, was visually striking, but it also carried implications that some observers found concerning. The geometry of the system suggested that we might be viewing it relatively close to face-on, meaning that if WR104 were to explode as a certain type of supernova that produces jets of energy along its rotational axis, one of those jets could potentially be directed toward our solar system. This possibility received considerable attention in various discussions, though subsequent analysis has suggested that the angle may be less threatening than initially thought, and the uncertainties involved in such calculations are considerable. Regardless of the specific geometry, WR104 represents another example of a star that exists in a state of profound instability, a star that will someday reach the end of its existence, and whose current state is unknown to us because the light we see is 8,000 years old. Much closer to home, at a distance of only 150 light-years, there exists a binary star system called Ik Pegasi, which presents yet another variation on this theme of stellar uncertainty. Ik Pegasi consists of two stars orbiting each other, one a white dwarf and the other a star somewhat larger than our Sun that will eventually evolve into a red giant. What makes this system particularly interesting is that when the larger companion does expand into its giant phase, it will likely transfer material onto the white dwarf, and if that white dwarf accumulates sufficient mass to exceed a critical threshold known as the Chandrasekhar limit, it could explode as a Type Ia supernova. At 150 light-years, such an explosion would be visible from Earth as an exceptionally bright star, though not close enough to pose any danger to our planet. The timeline for this potential event is measured in millions of years, making it far less imminent than the other candidates we have discussed, but Ik Pegasi remains on the list of systems that astronomers watch with particular interest, another star whose ultimate fate lies somewhere in the uncertain future. Each of these stars, Betelgeuse and Eta Carinii and WR104 and Ik Pegasi and others like them scattered throughout our galaxy, sends its light across the void toward our waiting instruments, and each packet of light arrives carrying information from the past, telling us how things were but not how they are. We observe them, we record their spectra and their brightness and their positions, and we build our models and make our predictions, understanding all the while that the fundamental delay imposed by the speed of light means that some portion of what we see may already be history, may be the afterglow of events that have already concluded in silence and violence far away. This is not cause for alarm but simply a condition of existence, a reminder that the universe operates on scales of time and distance that exceed our everyday experience, and that the light of the stars, so beautiful and so seemingly permanent, is always and forever a message from the past, arriving at last to tell us what once was, in places too distant to know what now is. When a star dies, the universe does not rush to tell us. The news travels at the speed of light, which sounds impossibly fast when you say it aloud, and yet light is patient in ways we sometimes forget. It crosses the vacuum of space at 300,000 kilometers per second, never slowing, never tiring, and still it can take thousands upon thousands of years to reach us here on this small blue world. So when we finally see a star's death, we are not witnessing something that is happening now, but rather something that happened long ago, in a place so distant that the very concept of now becomes slippery and uncertain. The light arrives like a letter from the past, carrying information about an event that concluded before your great-great-grandparents were born, before the pyramids were built, before humans first looked up and wondered what those tiny points of brightness might be. There is something rather peaceful in this arrangement, if you think about it in a certain way. The universe does not demand our immediate attention. It allows us to receive cosmic news on a delay, giving us time, in a sense, to prepare, though of course we rarely know that anything is coming until it arrives. And when death light finally does reach our eyes or our instruments, it unfolds with a strange gentleness, a brightening in the sky that seems almost polite in its announcement, as if the dying star wished to introduce itself before making too much of a fuss. On the night of February the 23rd, 1987, a man named Ian Shelton was working at Las Campanas Observatory in Chile, high in the Atacama Desert where the air is thin and dry and the stars shine with unusual clarity. Shelton was a Canadian astronomer, and he was engaged in the rather routine work of photographing the Large Magellanic Cloud, which is a small irregular galaxy that orbits our own Milky Way and is visible from the southern hemisphere as a faint smudge of light. The Large Magellanic Cloud sits approximately 168,000 light-years from Earth, which means that light leaving it today will not arrive here for 168,000 years, and light arriving here today left 168,000 years ago, when our ancestors were still learning to speak in complex sentences and had not yet dreamed of telescopes or observatories or the patient work of watching the sky. When Shelton developed his photographic plate that night, he noticed something unusual. There was a bright point of light in the Large Magellanic Cloud that had not been there before, a new star where no new star should be, and his first instinct was to assume that something had gone wrong with his equipment, because that is often the most reasonable explanation when the universe appears to do something unexpected. But the light was real. It was a supernova, the catastrophic death of a massive star, and it was the first supernova visible to the naked eye in nearly 400 years. Astronomers would come to call it SN 1987A, following the naming conventions that give each supernova a designation based on the year it was observed and the order in which it was discovered, and it would become one of the most studied objects in the history of astronomy. What made SN 1987A particularly special, beyond its mere visibility, was what had happened 3 hours before Shelton noticed that unexpected point of light on his photographic plate. Deep underground, in facilities designed to detect particles that pass through ordinary matter as if it were not there at all, instruments had registered something extraordinary. In Japan, beneath Mount Ikinoyama, the Kamio-Kande 2 detector, which consisted of a large tank filled with purified water surrounded by sensitive light detectors, had recorded 11 neutrinos arriving in a burst lasting just 13 seconds. And in Ohio, in a salt mine beneath Lake Erie, the IMB detector, which operated on similar principles, had recorded 8 more neutrinos in a burst of similar brevity. 25 neutrinos in total, which may not sound like very many, but neutrinos are ghostly particles that interact so weakly with matter that trillions of them pass through your body every second without ever touching a single atom. To detect 25 of them from a single source, all arriving within seconds of each other, was confirmation of something remarkable. Those neutrinos had been produced in the core of the dying star at the moment of its collapse, when the inner regions fell inward so rapidly and so violently that the density exceeded anything found elsewhere in the universe except inside black holes. They had streamed outward through the star's outer layers without resistance, because neutrinos care very little for ordinary matter, and they had begun their journey across 168,000 light-years of space. The visible light from the supernova, by contrast, had been trapped within the star's expanding envelope of debris for several hours, struggling to escape from the chaos of the explosion, and so it arrived at Earth slightly later than the neutrinos, even though both had traveled at or very near the speed of light. The detection of those neutrinos confirmed theoretical models that physicists had been developing for decades, models that predicted exactly this sequence of events, and it marked the beginning of a new kind of astronomy, one that could observe the universe not just in light but in particles that carry different information entirely. The star that produced SN 1987A had died 168,000 years before Ian Shelton photographed its light, and in a sense it had been dead all along. From our perspective, we simply had not received the news yet. The light that finally told us of its death had been traveling through space for all that time, crossing the void between the Large Magellanic Cloud and the Milky Way. And during that journey, entire civilizations had risen and fallen on Earth. Ice ages had come and gone, and countless generations of humans had lived and died without ever knowing that somewhere out there, a messenger of light was on its way. If you were to look up at the night sky tonight, you might see, in the right conditions and with a modest telescope, a faint smudge in the constellation Taurus that astronomers call the Crab Nebula. It is a cloud of gas and dust, roughly 11 light-years across, expanding outward at a rate of about 1,500 kilometers per second, and at its center sits a pulsar, which is a rapidly spinning neutron star that sends out beams of radiation like a cosmic lighthouse, rotating 30 times every second with mechanical precision. The Crab Nebula is beautiful in photographs, all filaments of glowing gas in shades of red and blue and green, and it is also the remains of a catastrophe. On the 4th of July in the year 1054 of the Common Era, Chinese astronomers recorded the appearance of a guest star in the constellation we now call Taurus. They noted that it was visible in daylight, which requires a brightness that few celestial objects ever achieve, and they observed it for 23 days as it slowly faded from that remarkable intensity. The guest star was a supernova, and it was roughly 6,500 light-years from Earth, meaning the star had actually exploded around 5,400 years before the Chinese astronomers saw it, during a time when the Egyptian pyramids were being built and writing was first being developed in Mesopotamia. The light had been traveling through space all that while, and when it arrived, it was bright enough to cast shadows. What the Chinese astronomers witnessed was the death of a massive star, and what we see today, nearly 1,000 years later, is the debris from that death, still expanding, still glowing, still carrying the energy of that ancient explosion outward into the cosmos. The Crab Nebula is a tomb and a monument, and it is also a laboratory, because astronomers have studied it extensively to understand how supernovae work and what they leave behind. The pulsar at its center is the compressed core of the original star, all that remains of something that once burned with the light of millions of suns, now reduced to a spinning ball of neutrons just 20 kilometers across. In November of 1572, something similar appeared in the skies over Europe, a new star in the constellation Cassiopeia that grew to rival Venus in brightness before fading over the following months. A Danish astronomer named Tycho Brahe observed this star carefully from his observatory on the island of Hven, in the strait between Denmark and Sweden, and his observations would prove to be among the most important in the history of Western astronomy. Tycho was meticulous in his measurements, using instruments of his own design to track the star's position with unprecedented accuracy. And he noticed something that challenged the accepted wisdom of his time. The star showed no parallax, which is the apparent shift in position that nearby objects display when viewed from different locations. If the new star had been close to Earth, perhaps in the atmosphere or somewhere between Earth and the Moon, it would have appeared to move against the background of more distant stars as the Earth rotated and as Tycho observed from different positions. But it did not move. It remained fixed among the other stars, which meant it must be very far away indeed, as far as the stars themselves. This was a problem for the astronomy of the 16th century, which held that the heavens beyond the Moon were perfect and unchanging, a realm of crystalline spheres carrying the planets and stars in eternal circular motion. The appearance of a new star, in a region that was supposed to be incapable of change, suggested that the heavens were not so perfect after all, that change and transformation could occur even among the distant stars. Tycho published his observations in a book called De Nova Stella, meaning on the new star, and the term nova, meaning new, would eventually be adopted to describe such events, even though we now know that they represent not the birth of new stars but the death of old ones. The supernova of 1572 is sometimes called Tycho's nova in honor of the man who studied it so carefully, and its remnant can still be detected today, a shell of expanding gas and dust roughly 20 light-years across, glowing faintly in X-rays and radio waves. The star that produced it was approximately 8,000 light-years from Earth, and its death light had been traveling toward us since roughly 6,000 years before the Common Era, when agriculture was first being developed in the Fertile Crescent and humans were beginning to build the first permanent settlements. 32 years after Tycho's nova faded from view, another bright star appeared in the constellation Ophiuchus. This was in October of 1604, and among those who observed it was the German astronomer Johannes Kepler, who would later become famous for discovering the laws of planetary motion. Kepler studied this new star for over a year, tracking its brightness and color as it slowly dimmed, and it became known as Kepler's star or Kepler's supernova in recognition of his work. It was the most recent supernova to be visible to the naked eye from Earth, which means that more than 400 years have passed since humans last saw a star die in our own galaxy without the aid of telescopes or other instruments. This is somewhat surprising, given what we know about the frequency of supernovae. Astronomers estimate that the Milky Way produces somewhere between 1 and 3 supernovae per century, on average, which suggests that several should have occurred since 1604. Some of these explosions may have been hidden from view by the dust and gas that fill the plane of our galaxy, absorbing and scattering light before it can reach us. Others may have occurred in parts of the sky that were not being watched, or during times when observations were disrupted by weather or war or simple inattention. Whatever the reason, we have been waiting for more than 4 centuries for another naked-eye supernova in our galaxy, and it is entirely possible that one has already occurred, somewhere out there in the spiral arms of the Milky Way, and its light is traveling toward us even now, crossing the vast distances between the stars at 300,000 kilometers per second, patient and unhurried and inevitable. Somewhere in the galaxy, perhaps thousands of light-years away, perhaps tens of thousands, a star has already died, and we do not know it yet. The collapse has happened. The core has compressed to unimaginable density. The outer layers have been blown outward in a shockwave traveling at a significant fraction of the speed of light, and the light from all of this violence is making its way toward Earth through the quiet dark. It may arrive tomorrow, or next year, or in 1,000 years, Or it may have been traveling for so long that it will not reach us for millennia yet to come. We cannot know, because the information travels no faster than light itself. And until the light arrives, the star appears unchanged in our sky, burning steadily, giving no hint of what has already transpired in that distant place. This is the nature of the universe, that it keeps its secrets for as long as the light requires to cross the emptiness between the stars, and then it reveals them all at once. A sudden brightening in the night sky, a guest star where none had been before, news from the distant past arriving at last after its long and lonely journey. And there is something calming, perhaps, in knowing that the universe operates on timescales so much vaster than our own, that the death of a star, which is among the most violent events that can occur in nature, reaches us as nothing more than a gentle point of light, a brightening that takes days or weeks to fade, a slow and peaceful announcement of something ancient and far away. When we turn our attention to the nature of time itself, and what it might mean for two events to happen at the same moment across the vast distances of space, we find ourselves entering territory that is both philosophically rich and gently disorienting in the most restful sort of way. The question seems simple enough at first glance. This idea of what is happening right now somewhere far away, and yet the more carefully we examine it, the more we discover that the universe operates according to principles that are quite different from our everyday experience of clocks and calendars and the comfortable feeling that the present moment is something shared by everyone everywhere all at once. Albert Einstein, working in the early years of the 20th century, developed his theory of special relativity through a careful consideration of how light travels and how measurements of time and space depend upon the motion of the observer making those measurements. One of the most profound and perhaps counterintuitive results of this work is the revelation that simultaneity, the idea of two events happening at the same time, is not an absolute feature of reality but rather depends upon one state of motion. Two observers moving relative to one another will disagree about which events are simultaneous, and neither of them is wrong, for the universe simply does not provide a universal present moment that everyone must share regardless of how they are moving through space. This means that when we ask what is happening right now on a planet orbiting a distant star, we are asking a question that does not have a single definite answer. The answer depends on the motion of the person asking, and this is not a matter of imprecise measurement or limited knowledge, but rather a fundamental feature of how space-time is structured. There is no cosmic clock ticking away somewhere in the depths of space, keeping track of a universal now that applies equally to Earth and to galaxies billions of light-years away. Each observer carries their own sense of the present, and these different presents are all equally valid according to the physics that governs our universe. The physicist Roger Penrose, in his explorations of the deep structure of reality, has discussed what is sometimes called the Andromeda paradox to illustrate just how significant these differences can become over cosmic distances. Consider two people standing quite close to one another on Earth, perhaps only a few meters apart, with one person walking slowly toward the Andromeda galaxy and the other walking slowly away from it. These two people are moving at extremely modest speeds, just the ordinary pace of a gentle stroll, and yet according to the mathematics of special relativity, their definitions of what is happening now in the Andromeda galaxy differ by a matter of days. This is a remarkable result to sit with quietly. The person walking toward Andromeda might define the present moment in that distant galaxy as being several days later than the present moment defined by the person walking away, and this difference arises purely from their relative motion, which is really quite slow by any ordinary standard. Over the 2.5 million light-years that separate us from Andromeda, Even small differences in velocity translate into substantial differences in which events are considered simultaneous. If there were intelligent beings going about their daily lives on a planet in Andromeda, one observer on Earth might say that they are currently sitting down to breakfast, while another observer standing nearby might say that they finished breakfast days ago and are now engaged in entirely different activities. Neither observer can claim to be correct in any absolute sense, for the universe does not privilege one definition of now over another. This is not a limitation of our measuring instruments or a gap in our knowledge that might someday be filled. It is instead a feature of reality itself, woven into the very fabric of space-time according to the best physics we have developed. The present moment, which feels so immediate and universal in our daily experience, turns out to be a local phenomenon that does not extend unchanged across cosmic distances. The philosopher Hans Reichenbach, working in the first half of the 20th century, explored these ideas in considerable depth and contributed to our understanding of what is called the conventionality of simultaneity. Reichenbach recognized that when we speak of two distant events happening at the same time, we are making a choice about how to define simultaneity, and this choice involves certain conventions that are not forced upon us by nature. We typically adopt the convention that Einstein used, which produces the results we have been discussing, but Reichenbach showed that other conventions are logically possible, even if they would make the mathematics more complicated and the physics less elegant. This philosophical work helps us appreciate that our intuitions about time, developed through millions of years of evolution on a small planet where we rarely encounter relative velocities that approach the speed of light, do not necessarily reflect the deepest truths about how the universe operates. Our ancestors had no need to understand relativistic effects in order to survive and reproduce, and so our brains came equipped with a model of time that works beautifully well for everyday purposes but requires significant revision when we contemplate the cosmos as a whole. There is something rather peaceful about this realization, this acknowledgement that the universe is under no obligation to conform to expectations that evolved for entirely different circumstances. The astronomer and science communicator Carl Sagan, in his landmark television series Cosmos, which first aired in 1980, offered a poetic reflection on our relationship to the stars that still resonates today. Sagan observed that we are made of star stuff contemplating the stars, a phrase that captures something profound about our cosmic situation. The atoms in our bodies, the carbon and oxygen and iron and all the other elements that make up our tissues, were forged in the nuclear furnaces of stars that lived and died long before our solar system formed. When we look up at the night sky, we are in a very real sense looking back at our own origins, at the stellar generations whose deaths made our existence possible. This perspective adds another layer of meaning to our contemplation of cosmic time. We are not separate from the universe we observe, but rather deeply embedded within it, made of the same materials that constitute the distant stars and connected to them through chains of cause and effect that stretch back billions of years. The light arriving at our eyes tonight has traveled across such immense distances that it carries information from epochs when our constituent atoms were still part of other stars, other worlds, other configurations of matter and energy entirely. When scientists engaged in the search for extraterrestrial intelligence, often abbreviated as SETI, consider the possibility of detecting signals from intelligent civilizations elsewhere in the galaxy, they must grapple directly with the implications of cosmic time. If a radio signal were to arrive from a planet orbiting a star 1,000 light-years away, carrying perhaps the equivalent of a greeting or a statement of existence, we would know that the signal was transmitted 1,000 years ago. In the time since that transmission departed its home world and traveled across the vast gulf of interstellar space, civilizations could rise or fall, technologies could advance beyond recognition, wars could be fought, plagues could sweep through populations, or perhaps peace and flourishing could unfold across a millennium of development. The senders of such a signal, whoever they might be, would have no way of knowing what Earth would be like when their message arrived. They would be broadcasting into the unknown future, trusting that someone, somewhere, might be listening when their electromagnetic whisper finally reached its destination. And we on Earth, receiving such a signal, would be confronted with the strange situation of hearing from beings about whom we know only what they were like 1,000 years ago, with no way to determine their current state or even whether they still exist. The conversation would be one conducted across time as much as space, a dialogue in which each participant speaks to the past of the other and can only hope that the future holds listeners. In December of 1995, the Hubble Space Telescope was pointed at a seemingly empty patch of sky, a region that appeared dark and featureless to ground-based observations, and held there for approximately 10 days of total exposure time accumulated across many orbits. The resulting image, known as the Hubble Deep Field, revealed that this apparently empty region was in fact filled with thousands upon thousands of galaxies, each one a vast island of stars comparable in scale to our own Milky Way. The observation demonstrated that wherever we look in the cosmos, as long as we look deeply enough, we find galaxies upon galaxies extending to the limits of detection. Many of the galaxies visible in the Hubble Deep Field lie at distances of approximately 12 billion light-years, which means we are seeing them as they existed 12 billion years ago, when the universe itself was only a fraction of its current age. At that time, the cosmos was a younger and quite different place. These distant galaxies appear as small, irregular, infant structures, still in the early stages of their formation, not yet grown into the grand spiral and elliptical forms that characterize mature galaxies in the present-day universe. The light that formed their images on the telescope's sensors departed those galaxies when they were cosmic infants and has been traveling toward us ever since, crossing an expanse of space so vast that trying to conceive of it directly is rather like trying to imagine an unfamiliar color or a new sense altogether. Those galaxies have not remained frozen in time while their light was traveling to us. In the 12 billion years since that light departed, they have continued to evolve, to merge with other galaxies, to form new generations of stars, to undergo all the processes that govern galactic evolution over cosmic timescales. The structures we see in the Hubble Deep Field no longer exist in the forms we observe. They have long since transformed into mature galaxies, perhaps spiral galaxies much like our own, perhaps giant ellipticals formed through the collision and merger of multiple smaller galaxies, perhaps configurations we cannot easily predict from our current understanding. When we look at the Hubble Deep Field, we are not seeing those galaxies as they are now, because there is no universal now that would give such a statement clear meaning. We are instead seeing those galaxies as they were in their youth, and we can only infer what they might have become through our understanding of how galaxies generally evolve over time. The image is a window into the distant past, a record of conditions that prevailed billions of years before Earth formed, billions of years before the Sun ignited, billions of years before the atoms in our bodies were assembled by previous generations of stars. This is true not only for the extremely distant galaxies in deep field observations, but for everything we see when we look up at the night sky. The night sky is not a window showing us the current state of the cosmos spread out before us in its present configuration. It is instead something more like a time machine, with each direction showing us a different era of cosmic history depending on how far away the objects in that direction happen to be. The Moon appears to us as it was about 1¼ seconds ago. The Sun appears as it was roughly 8 minutes ago. The nearest stars beyond the Sun appear as they were years ago, and more distant stars appear as they were centuries or millennia ago. Looking toward the center of our galaxy, we see light that departed that region approximately 26,000 years ago, when our ancestors were painting on cave walls and the development of agriculture still lay far in the future. Looking toward Andromeda, we see light that departed over 2 million years ago, when early human ancestors were just beginning their long evolutionary journey. Looking at the most distant galaxies visible to our telescopes, we see light that departed when the universe was young and hot and filled with conditions utterly unlike those we experience today. Every direction we look, every object we observe, shows us a different moment in cosmic history. The night sky is stratified by time, with nearby objects showing us the recent past and distant objects showing us epochs stretching back toward the origin of the universe itself. There is something quite soothing about contemplating this arrangement, this realization that when we step outside on a clear night and look up at the stars, we are participating in a kind of cosmic archaeology, passively receiving information from across the ages simply by allowing light to enter our eyes. And so we return now to where we began, standing or perhaps lying beneath the night sky, though now we carry with us a quieter understanding of what we are truly seeing when we lift our eyes to those scattered points of light. The darkness above you is not empty, not truly, for it is filled with travelers, with ancient messengers making their way across distances so vast that the mind cannot hold them except as abstractions, as numbers written on pages that seem to belong more to poetry than to physics. Each photon arriving at your eye has completed a journey that began long before you drew your first breath, long before your parents met, long before your grandparents walked upon this earth, and in many cases long before the stones of the oldest human structures were quarried from hillsides and shaped by hands that have been dust for millennia. When you look at a star of the 6th magnitude, which is to say a star just barely visible to the unaided eye on a clear dark night, approximately 100 photons from that star enter your eye each second. 100 tiny parcels of light, each one having traveled for years or centuries or longer, each one carrying the same energy it possessed at the moment of its creation in the nuclear furnace of a stellar core. This is not a flood of light but rather a gentle rain, a soft accumulation that your retina gathers and your brain assembles into the perception of a faint but unmistakable point of brightness against the dark. Those 100 photons per second represent the survivors, the ones that happen to be traveling in precisely the right direction across all those light years to intersect with the small wet sphere of your eye at this particular moment in the long history of the cosmos. Consider for a moment what those photons have passed through on their journey to reach you, and the answer, remarkably, is almost nothing at all. The space between stars is not filled with air or water or any medium through which the light must push and struggle. It is vacuum, as close to perfect emptiness as anything in nature can achieve, a void so complete that a photon can travel for 1,000 years without encountering a single atom, without being absorbed or scattered or deflected from its path. The light that touches your eye tonight has crossed this immense nothingness, this cathedral of absence, carrying its tiny freight of energy across distances that would take our fastest spacecraft tens of thousands of years to traverse. And it has arrived unchanged, undiminished in its essential nature, still vibrating at the same frequency it possessed when it left the surface of a star that may no longer exist. There is something profoundly comforting in this thought. though it requires a certain gentleness of mind to perceive it. The Japanese have a phrase for this quality of feeling, this particular texture of emotion that arises when we contemplate the beautiful and the fleeting together. They call it mono no aware, which translates imperfectly into English as something like the gentle sadness of impermanence, or perhaps more accurately as the pathos of things, the bittersweet awareness that all beautiful things are passing, that the cherry blossom is more beautiful because it falls, that the autumn leaves are more precious because they fade. This concept does not counsel despair but rather a deepening of appreciation, a recognition that transience and beauty are not opposed but are instead intimately related, each making the other more vivid and more dear. When we look at stars that no longer exist, we are practicing a kind of mono no aware on a cosmic scale, finding beauty in light that has outlived its source, in messages that have arrived after the sender has departed. The star that created this light may have exploded in a supernova thousands of years ago, scattering its enriched materials across space to become the raw ingredients of new stars and new planets. Yet its light continues to arrive, continues to complete its ancient errand, unaware in any meaningful sense that its origin has ceased to be. There is gentleness in this, a softness that the facts of astronomy do not diminish but rather deepen, for we are reminded that endings and beginnings are not always synchronized, that the effects of beautiful things can persist long after their causes have transformed into something else entirely. The American astronomer Maria Mitchell, who lived from 1818 to 1889 and who was the first professional female astronomer in the United States, understood something important about the relationship between scientific knowledge and the human capacity for wonder. She discovered a comet in 1847. She taught at Vassar College. She traveled to Europe to visit observatories and to meet with the leading astronomers of her day. And throughout her life she maintained that the study of the heavens required not merely precision and patience, but also a quality of mind that could reach beyond the immediately measurable. We especially need imagination in science, she wrote, recognizing that the facts alone, however carefully gathered and recorded, are not sufficient to convey the full meaning of what we observe when we turn our instruments and our eyes toward the sky. The imagination she spoke of is not fantasy or wishful thinking, but rather the capacity to hold in mind realities that exceed our direct experience, to feel the truth of distances we cannot walk and times we cannot live through, to understand in some visceral way what it means for light to travel for 1,000 years through emptiness and arrive at last at the eye of someone standing on a small planet in an unremarkable corner of an average galaxy. This need for imagination in science is perhaps nowhere more evident than in our attempts to comprehend our own smallness in the vastness of space. And there is no image that conveys this smallness more eloquently than the one captured by the Voyager 1 spacecraft on the 14th of February in 1990. At that time, Voyager 1 was approximately 6 billion kilometers from Earth, having spent more than 12 years traveling outward through the solar system after its launch in 1977. At the request of the astronomer Carl Sagan, the spacecraft turned its camera back toward the inner solar system and captured a series of images that included, in one frame, the Earth itself. In that image, our planet appears as a single pixel, a pale blue dot suspended in a beam of scattered sunlight, so small that it would be easy to mistake for a camera artifact or a speck of dust on the lens. Everything that has ever happened in human history, every war and every peace treaty, every birth and every death, every symphony composed and every field planted, every love affair and every heartbreak, all of it took place on that single point of light, that tiny mote adrift in the cosmic dark. The pale blue dot image, as it came to be known, was not a scientific measurement in the usual sense, for it told us nothing we did not already know about the Earth's size or position or composition. Its value was imaginative and emotional, a way of helping us feel what we already knew intellectually, that our planet is small and our place in the universe is modest, and that the light of distant stars has been traveling since long before anything on this pale blue dot learned to wonder about where that light came from. When you lie beneath the night sky and watch the stars, you are engaging in an act of imagination not unlike the moment of looking at that single blue pixel and understanding that it contains everyone you have ever known and everything you have ever loved, all rendered almost invisible by the simple fact of distance. And yet this smallness is not a cause for despair but rather for a curious kind of peace, the same peace that comes from understanding that the universe does not depend upon our importance, that it will continue in its vast and patient way regardless of our worries and our plans, and that we are free to simply witness its beauty without the burden of believing that everything depends upon us. The stars do not need our attention to shine. The photons do not need our awareness to complete their journeys. And the light from vanished stars does not need our grief to continue arriving night after night at the eyes of anyone who cares to look upward. We are witnesses to something that would happen whether we watched or not. And there is comfort in this. The comfort of participating in something so much larger than ourselves that our individual concerns become, for a moment, as weightless as the photons themselves. The light from distant stars has survived things that would destroy anything we have ever built, crossing the cold between galaxies, passing through regions where the temperature approaches absolute zero, traveling for time spans that make the entire history of human civilization seem like a single heartbeat. And yet this light is fragile too, in its way, for each photon is a discrete thing that can be absorbed by a single atom, stopped by a single collision after a journey of 1,000 years. The photon that enters your eye tonight will be absorbed by a molecule of rhodopsin in your retina, will trigger a chemical change that sends an electrical signal to your brain, and in that moment its journey will end, its energy transformed into the experience of seeing a star. You are the end point of a voyage that began before you were born, the destination toward which that tiny packet of light has been traveling since before your great-grandparents were children. And in receiving it you complete a circuit that spans centuries and light years and the absolute emptiness of interstellar space. So as you settle now toward sleep, let this knowledge be a comfort rather than a burden, a soft blanket of understanding that the universe wraps around those who take the time to wonder about it. The stars above you are not merely points of light but messengers from the past. And some of them are messengers from sources that no longer exist, gifts from vanished suns that continue to arrive long after the givers have transformed into something else. The light carries no urgency, no demand that you stay awake to appreciate it, for it has waited millions of years already, and it does not mind if you close your eyes and drift toward dreams while it continues to fall gently upon the world. There will be more light tomorrow night, and the night after that, an endless slow rain of ancient photons arriving from stars both living and dead, falling upon oceans and forests and cities and the closed eyelids of sleepers who have carried their wonder into the country of dreams. The sky is both ancient memory and present miracle, a record of the past written in light that is nevertheless arriving only now, only in this moment, completing journeys that began in the deep past but that are ending here, tonight, in the soft darkness where you rest. Even vanished stars leave gifts of light still arriving, still carrying their warmth across the void, still offering themselves to anyone who cares to receive them. And you have received them. You have let them enter your eyes and your mind and your imagination. And now you may let your thoughts grow soft and quiet. knowing that the universe continues its patient work while you sleep, that the light continues to fall, that the distances continue to be crossed by travelers too small to see but no less real for their invisibility. Rest now among the ancient lights, which will go on arriving whether you watch them or not, which will be there when you wake, which will continue their long journeys through the emptiness for millions and billions of years after everything we know has changed into something else entirely. There is peace in this continuity, peace in this patience, peace in knowing that the cosmos does not hurry and neither must you, and that the light of dead stars is still light, still beautiful, still falling gently on a world that is small and precious and wrapped in the darkness of a night that is filled, absolutely filled, with ancient gifts traveling home at last.